Okay, so manje sizokwenza le question le yalo ethi. Okay, let me just read the question. A boy on ice skates is stationary on a frozen lake. There's no friction there. And then he throws a package of mass 5 kg at 4 meters per second, horizontally east as shown as shown below, right? So just look at that picture there. And then the mass of the boy is 60 kg, right? And then but at the instant the package leaves the boy's hand, the boy starts moving. Okay? And then 4.1, but in which direction does the boy move? And then write down east or west. So if he's drawing package layer go eastern direction, because so ugcoke ama skates, ma roller skates or ma skates, right? Sitting ma skates on a frictionless surface. So there's no friction there. As it throws the package, he slightly moves. So we move away in direction. He throws the package in that direction. Therefore, it makes sense to move to the other direction. This is an application of Newton's third law of motion. He exerts a force on a package in that direction. Therefore, the package will exert the same force to the boy, but in the opposite direction. So he'll exert a force in that direction. So he package move to that direction. The package will exert the equal force in the opposite direction. So now also move to the west. It's application of Newton's third law of motion. So 1 is west. Okay, and then 4.2. But which one of Newton's law of motion explains the direction in which the boy experiences a force when he throws the package? Name and state the law in words. It's Newton's third law of motion, right? So it's Newton third law of motion, right? It states that when object A exerts a force on object B, then object B will exert the equal force or the same force on object A, the same force on object A, the same force on object A in the opposite direction. That's Newton's third law of motion. Okay, and then ruler lapos 4.3. But which one of 4.3. But calculate the magnitude of the velocity of the boy immediately after the package leaves his hand. Ignore the effects of friction. We ignore the effects of frictions, meaning the net external force is 0. So we have a closed system. Therefore, if we have a closed system, we can apply the principle of conservation of linear momentum, right? So this is an explosion type of question. So ngishilo momentum, you have collisions, you have explosions. Kuma collisions, you have two separate objects moving towards each other, and then after they collide, maybe they can bounce back to different opposite directions, or they can move together as a unit, right? And then kuma explosion, these objects they start as a one thing. So suppose like ngifuna uphonsa le phone to that direction, so that will be an explosion type of question, because before ngiphonsa to that direction, me and this phone are one unit, because it will be the mass of the phone plus my body mass. Then we are one system, and we have an initial velocity of 0 because I'm not moving, I'm standing. Then as I move, I throw this phone in that direction. The mass of phone say was separated from my body mass. So if phone say object on its own, and then my mass is separated from him as a phone, and then mina senye object on my own. And then if I'm standing on a frictionless surface and I'm ngogama skates, and then I roll back to the opposite direction. So this is what is happening here, right? And then we can apply principle of conservation of linear momentum to explain the situation and solve for the unknown velocity, right? So the total linear momentum before is equals to the total linear momentum after, right? So before, it's the mass of the boy plus the mass of the package. So it's the mass of the boy plus the mass of the package and their initial velocity. And then after, it will be the mass of the boy times his final velocity plus the mass of the package times its final velocity. Okay, so we are told the boy is 60 kg, the package is 5 kg, and then their initial velocity will be 0 because initially they are stationary, and then the mass of the boy is still 60, and then the final velocity of the boy is what we want to calculate, and then the mass of the package is still 5, and then we'll assume its direction to the east as positive, right? And then so the velocity of the package is 4 meters per second east, right? So now I can solve for the velocity of the boy. So the velocity of the boy will be minus 20 divided by 60, right? Minus 20 divided by 60 will be, let me pull my calculator, minus 20 divided by 60 will be minus 1 over 3 or minus 0.33 meters per second. So the boy will move 0.33 meters per second west, right? So that will be his final velocity. Okay, and then say 4.4. 4.4, but how will the answer to question 4.3 be affected if the boy throws the same package at a higher velocity in the same direction? So suppose that I'm standing on a frictionless surface, I'm wearing skates, and I have a package. First I throw the package away at a velocity of 4 meters per second. Now let's say this is the force that I'm applying. Now if I want to increase the velocity at which this package leaves my hand, I'll have to apply a greater force to that package so that I can speed up its velocity, so I can increase its velocity. So I apply a greater force on the package. According to Newton's third law, the package will apply the very same force on my body in the opposite direction. So the velocity will have to increase, because to increase the velocity at which I'm throwing the package, I'll have to apply a greater force to increase that velocity, right? And then as I apply a greater force, the package will apply the very same greater force on my body. Then I'll have to move back at a greater velocity. So there the answer will have to be greater than, or it will have to be, it increases, right? It increases. Okay? And then that's 4.4.1. 4.4.2. The boy throws a package of double the mass at the same velocity as in question 4.3 and explain the answer. So now I'm throwing so this is another situation. I'm throwing a different package now. It has a greater mass than the initial one. But then as I throw it, it will have the velocity, the same velocity as the original package. So let's say the package color is package A. It's package A, and then this is the boy. He throws the package. This is for it's 5 kg. So it's 5 kg. right? And then it throws the package, it moves 4 meters per second east. Ne? And then now there's another situation now. So this is the boy. He throws package B now of a bigger mass. Let's say the mass is 10 kg. Double the mass. I think double the mass, ne? Yeah, double the mass. So if you double the mass, it will be 10 kg. So it's a bigger package now, it's 10 kg. That one is 5 kg, this one is 10 kg. So he throws the package away, and then it moves at the same velocity as the original package. So they want to know what will happen to the... So case 1, he throws the package of 5 kg, and then as it leaves its hands, it leaves at 4 meters per second. And then he moves in the opposite direction as 0.33 meters per second. Right? So now if you double the mass of that package, they want to know what will happen to his velocity. Sorry, what will happen to his velocity? Will his velocity be bigger than 0.33, or will it be less than 0.33? So I would say, okay, since he's throwing a bigger package at the very same speed in the eastern direction, because it's a bigger package now, in order for this package to have the same velocity as this smaller package, he will have to apply a greater force to this bigger package than he did with a small package if he wants to maintain the same velocity, right? So if he applies a greater force on this package will have to apply a greater force on this boy in the opposite direction, according to Newton's third law of motion. So his velocity will have to be greater than when he throws this smaller package at a velocity of 4 meters per second. I hope it makes sense. But because this package is bigger, he will have to apply a greater force on this package to maintain the very same velocity. And then because of Newton's third law of motion, this package will apply a greater force, and then he will move back at a greater velocity. Okay? So yeah. If I double the mass, then again, if I double the mass, I will have to be increasing a change in momentum, because if I double the mass of this object, and then momentum is dependent on mass and velocity, right? I keep the velocity the same, but then I increase the mass. So this will have to be a greater momentum, right? This is object A, this is object B. Object B, if velocity it's both 4 meters per second, but then I'm doubling the mass. So I'll have to increase the momentum, right? If I double the mass, momentum is will increase, right? So if I increase the momentum, then because of impulse momentum theorem, the change in momentum will increase as I increase this, right? The change in momentum will have to increase. So if I increase the change in momentum, F net is directly proportional to change in momentum. So F net will increase. If I increase F net, therefore that velocity will have to increase as well. So I don't know how to, if I was resisting, then I don't know how else to explain it. But then so if we were to write it down, Zoti, it increases, right? Zoti, if we double the mass and fix velocity, then the boy will need to apply a greater force. Therefore, the object will also apply the same force in the opposite direction. Therefore, his velocity will increase. I hope it makes sense. Yeah, so I will end it here. And if you corner long as you corner, like, apply your common sense. It should be clear. If you increase the mass of an object and then you keep velocity the same, then the velocity of the boy will have to increase from 0.33 to something else. Okay, so yeah.